Good morning, everybody, and welcome to today's ECR presentation by Dr. Tsukasa Yoshinaga. And the topic of the presentation is a computational framework of human voice production, muscle activation simulation in male and female voices. So let me introduce the speaker a bit. Dr. Yoshinaga is a visiting scholar working with Professor Yan Zhang in the head and neck surgery department at UCLA. He received his Ph.D. in mechanical engineering from Osaka University, where he is currently an assistant professor, and he will be going back there in April. I just learned. Um, and his research focuses on sound generation mechanism in human speech and musical instrument using numerical simulation. So this is very exciting topic. Hope you enjoyed the presentation. And with not much otherwise, and over to you, doctors.
Thank you very much for your introduction. So let me share the slides. So thank you for your introduction. My name is Tsukasa Yoshinaga from Department of Head and Neck Surgery. And today I'd like to talk about the computational framework of human voice production with muscle activation simulation in male and female voices. So first, when we consider the human voice production, we use vocal cords or vocal folds located in our larynx at the center of our throat, as shown in the left picture. You can see the red rectangle. This is a larynx, and when we cut the plane here at the center like this, then you can see this kind of like muscle and tissue inside our throat. And at the center, you can see the vocal folds. And when the airflow is coming from the lung, these vocal folds vibrate left and right. And this vocal folds vibrate at a frequency of like 100 to 200 hertz in normal phonation. And this vibration can be seen like this. This is a high-speed imaging of the laryngoscopic view. The camera is put from the above the vocal folds, and this kind of special like wave type vocal fold motion produce the characteristic sound of the voice. And as you can see in the picture, there inside the vocal folds there are many like ligaments and the muscles. And by activating these muscles, we can change the shape of the vocal folds and we can create wide variety of voices. And also in different persons, they have different voice qualities. Like you can hear the difference of male and female in the voice. And also one person can produce many kind of voice. Like when you try to imitate other person's voice, you can change the voice characteristics. And when we consider the voice characteristics, there are several factors to regulate these voices. And these are the main three factors. First, we need to control the subglottal pressure. Subglottal pressure is pressure between these vocal folds and the lung. So when the airflow is coming from the lung and when the vocal folds was closed, the pressure below the vocal folds that's increased, and this is called subglottal pressure. And this pressure can influence the loudness, pitch, and the stability of the voice. And the second main important factor is vocal fold characteristics. So as you see in this picture, the vocal folds consists of the muscle. So we can change the shape of the vocal folds. So geometry and the mechanical property of the vocal folds change the waveform passing through the vibrating vocal folds. And so this can change the main sound source of the voice. And the third factor is the vocal tracts. So when we speak, we change the shape of the mouth by changing the position of the tongue or jaw. And we can change the sound like RE, this kind of change in the sound by mainly acoustics. But sometimes there's effects of aerodynamics by changing the vocal tract shapes. So first, let me introduce about the effects of vocal tracts. So when we speak, this is a real-time MRI observed in we observe the tongue shape in the speech. So you can see like the tongue is moving very fast, and when we speak and we control the voice with acoustics, and when we speak like this, the vocal cords is vibrating out here in the larynx, and mainly this change in the shape of the mouth differs the type of the vocal the type of the phoneme like IU, but there is sometimes aerodynamic effects that change the vocal cord vibration. So this is the results in our simulation that's showing the recent simulation that's showing the effects of the constriction on the airflow in the vibrating vocal cords. So here is the vocal cords vibrating left and right, and if there is a constriction like this in the just above the vocal cords, this change in the vocal tract shape can influence the airflow passing through the vocal cords, and this change in the airflow can change the vocal cord vibration characteristics, and this vibration characteristic changes the airflow passing through the vocal cords, and this interaction can change the voice characteristics. But this is very special case, and you need many like special technique to change such vocal tracts like false folds. Like this is just the folds just above the vocal folds, and you cannot usually change this type of this vocal tracts to make the different voice characteristics. But sometimes like singers can produce special voice with such vocal tract and produce special voice. But mainly the vocal tract affects in the acoustic way. So in the normal person, we change the voice quality by changing the vocal cord vibration characteristics. And this is coming from the changing the vocal tract shape or geometry or like the stiffness, mechanical property in the vocal cords. And this is the example of 3 types of the vocal cords vibration. And the upper figure shows the vibration airflow, and the lower part shows the spectrum sound produced by this airflow. And from the left, I show the change of the waveform in the airflow, and you can see that this waveform does not go to 0, and the airflow continuously flowing through the vocal cords, vibrating vocal cords, and this sound can be here like this. So this is called breathy voice, and because the vocal cords does not close completely, the sound source is mainly produced from the turbulent airflow, and the sound become very breathy. And but if you can close the vocal cords completely, the airflow become like this, that when the vocal cords completely closes, the flow goes to 0, and the increase when the vocal cords open, and by repeating these waveforms, you can produce more normal voice, which can be here like this. So the like harmonics of the sound can be like much larger than the breathy voice, and you can hear more normal voice. But if the vocal cords closes too much, then this is called pressed voice, and the waveform becomes smaller than the normal vibration, but and the closing phase is much longer, but sound can be here like this. So this pressed voice is produced by the strong closure. And the recent simulation by Professor Zhang shows that this change in the voice characteristics is mainly coming from the vertical thickness of the vocal cords, and shown in this picture. This change in this vertical thickness causes such change in the airflow vibration, and when the vocal force is too thin, the vocal cord cannot close completely and this bracy voice is produced. And when the vocal fold is too thick, then the vocal fold closes too much and this kind of pressed voice is produced. So we have already known that this vocal fold thickness is very important in changing the vocal fold vibration characteristics, but we still don't know what is the factor of changing this vocal fold thickness. So when we consider about the change in the vocal fold shape, we have to consider the anatomy of the larynx. And this is a picture of the anatomy of the larynx. And mainly there are 3 cartridges and 5 laryngeal muscles that controlling the vocal fold shape. And as you can see here, at the bottom of the larynx, there's a cartridge called cricoid at the bottom that is connected to the trachea. And from above here, there's a thyroid cartridge. This is large one. It's located just above the cricoid. And the front part of the vocal fold is connected this thyroid. And the third cartridge is called arytenoid, and this is located at the inside of the thyroid. And this is the back part of the vocal folds. And by changing the position of these cartridges, you can change the shape of the vocal folds. And there are also many laryngeal muscles that controlling the position of the cartridges. And it's called like cricothyroids that's connecting the cricoid and thyroid, or other like 4 muscles located around the arytenoid cartridge that change the position of the arytenoid. And the vocal fold itself has a muscle called thyroarytenoid, which is connected between thyroid and arytenoid. So vocal folds can open and closes with these muscles, but also can change the vocal fold shape itself with this muscle. So in previous studies, there are observations of change in the vertical thickness. So this is examples. And in the old paper in Journal of Voice, Professor Hirano shows that how the vertical thickness of the vocal fold will be different depending on the simulation of the muscle, TA muscle, located just inside the vocal folds. And you can see this is the vertical thickness. So from the control without the electric stimulation of the muscle, the thickness is from here to here. But when the muscle is stimulated, the vertical thickness significantly increased from here to here. You can see that. So he cuts the vocal folds at the center here like this, and he observed how the vertical thickness will be different. And also in the recent exercise canine larynx experiment, they extracted half of the larynx, like this picture, and they visualized how the muscle activation changed the vocal fold shape in this movie. And they show that with activation of TA muscles, this vertical thickness is significantly increased, like this. So we know that the activation of this muscle, TA muscle, is very important to change the vertical thickness to control the voice quality. But we still don't understand why the mechanisms of the why this like muscle can change the vertical thickness. So we conduct a mechanical modeling simulation to understand the mechanisms of this deformation. So before going to the mechanical modeling, I would like to explain why we need the mechanical modeling. So in the recent advancements in AI technology have dramatically improved the speech synthesis and speech recognition in the commercial products like Google and things like Amazon something. And these advancements in neural speech synthesis have been made possible by large amounts of speech data. So they use large amounts of speech data to train the machine learning model, and they could produce such natural speech. But our main goal is to gain insights for voice rehabilitation and the voice training. So we cannot use such kind of machine learning model to treat the patient in the head and neck surgery department to for the persons like who has speech disorders or like who wants to sing with more good voice quality, they cannot use such data. And we want to gain more insights to how we can control the voice quality or how we can improve the voice quality. So we need to understand mechanism to get insights for such rehabilitation. And also to obtain such insights, we need lots of data from the like stimulation of the muscles or like the anatomy of our voice, but we cannot get a lot of data for such like anatomy or like muscle activation in the real human speakers because of the technology and the ethical issues. So we cannot make such machine learning model to understand the mechanisms, but by doing the mechanical model, we can maybe in the future, we can make the machine learning model to train to simulate the muscle activation. But from here, we don't have such data, so we try to make the mechanical modeling to understand the change in the vocal fold shape. So here's the method of how we did the mechanical simulation. So we first extracted the geometry from the medical imaging. So we used the super resolution MRI with resolution 0.1 millimeter. So you can see the change in the tissue color and the ligament or the cartridges inside this picture. So we segmented each muscle on the cartridges like this. And by doing this segmentation in each slice of the MRI, we can obtain this kind of three-dimensional geometry. So you can see the white color with the cartridges, like thyroid, arytenoid, and cricoid, these three cartridges, and other soft tissue and muscle color in like here TA and other muscles are located as observed in the MRI. And here is a comparison. We use one male and one female for this study. And here's the top view and the side view of the larynx. And as you can see, overall shape is quite similar between male and female, but there are some differences. And my main thing is that the size of the vocal cords is different. The vocal cords is located here, and the length of the male is like 20 millimeter, but in the female, the length was 15 millimeter, and the female has shorter vocal cords because the larynx has a smaller shape. And also the other difference is the angle of the vocal cords was different. The male has more vocal cords aligned to x-axis, while the vocal cords in female is inclined towards the z-axis like this. So there was a difference in angle between male and female. So here's how we did the computational modeling. So we solve the equilibrium state, equilibrium equation shown here by like considering the muscle force or muscle stress activated in the model, and we did the iteration calculation by reaching the equilibrium state to obtain the final state of the muscle geometry. And we consider the strain energy density function to consider the large deformation in the simulation. And this function has a passive component and active component. And for the passive component, we consider the anisotropic model for the vocal cords muscle here, TA and the cavalier. We have the different stiffness along this axis and on this axis. And the other muscles was modeled with the isotropic muscle for the simplicity. And here we use this kind of function to simulate muscle activation. By changing this value from 0 to 1, we can simulate the gradual change of the geometry by gradually increasing the stress of the muscle. And here is how we obtain the material properties. In the previous study, the professor then did the biaxial tension test for the vocal folds, and he put in two directions. The vocal folds was put at the center, and he could obtain the strain stress curve like this in the anterior posterior direction, the transverse direction. And so with this, by fitting the stress strain curve here, we can consider the difference, the stiffness between like horizontal axis and the vertical axis. And here is the boundary conditions. We set the three cartridges as a linear elastic model material with a very large value of the Young's modulus, so that the muscle activation cannot change the shape of the cartridge. And the boundary condition on the thyroid, this large cartridge was set to just allow the movement in back and forward and the rotation along this CT joint. And the bottom, the cricoid was fixed, and the joint between this arytenoid and cricoid was set by the motion defined with this line here shown to reproduce the motion of the arytenoid with this joint. So we solved this equation by using the finite element method, and we constructed this kind of tetrahedral elements, and the total number of elements is like 50,000 elements. And we stimulated each muscle to get the equilibrium state. And here is the first validation with the experimental observation. The upper panel shows the observation in the in vivo canine larynx. The experiment has been done by the Chatri, and he compares the final state to the vocal fold shape by activating each muscle in the in vivo canine larynx. And we compared this shape in the bottom with the simulation. And the color shows the displacement of each element. And by stimulating TA, you can see the closure at the front part, and the back part is still open. And this shape change can be quite similar. It's quite similar between experiment and the simulation. And by activating CT here, the vocal folds was elongated as shown in the experiment. And also, when we activate IA and LCA, the back part was closed and the front part was still open, and this was also reproduced in the simulation. And finally, when the three muscles was activated, all part of the vocal folds were closed, and this was also quite similar to the experimental observation. So we could validate whether this modeling was accurate for reproducing the shape change of the vocal folds. So here we compare the difference between male and female. And here also shows the displacement in color. And you can see that the overall shape or displacement were quite similar between male and female. Male is upper part and the female is lower part. And also the length change in the vocal folds was quite similar. Like when the TA muscle here was activated, the vocal folds became shorter, like 13% for both larynx, and in the CTF muscle was activated here, then the elongation of the vocal folds was also quite similar between male and female. And finally, we compared the shape of the cross-section, the vocal folds, with the TA muscle activation. So in the previous study, we observed the large change of the vertical thickness as shown here. And here we compare the same cross-section, male in upper panels and female in lower panels. And by activating TA, the lower part of the vocal folds is going towards the medial center line here in the female larynx. But in the male larynx, the overall shape was like enlarged because the vocal folds was shortened and the overall volume was same, so this cross section was enlarged towards the upper side, but vertical thickness was almost same from the beginning in the male larynx. So we could not reproduce the shape change like this in the male larynx. So we explore why we could not reproduce this kind of change in the male larynx. So first we changed the geometry, initial geometry and the muscle attachment in the male larynx because we thought maybe the initial extraction in the MRI might have the errors, and we also add the like soft tissue in between the muscle and the cartilages, but this could not reproduce the change in the vertical thickness. So next we changed the constitutive law and the joint modeling as shown here. Like this joint modeling limits the shape change in the vocal folds. So we slightly changed these conditions, but we could not reproduce the vertical thickness. So finally, as we observed in the initial shapes, we changed the fiber orientation here. The female has more inclined angle of the muscle fiber in the this larynx, and you can see the difference in the angle. So maybe we thought that this fiber angle is very important in the change in the vertical thickness. So we parametrically changed this fiber angle in the model. So here we change the fiber angle. We change the 595 degree. So first, the previous results were modeled with the initial angle of the 4 degree in the male larynx based on this initial geometry, and the female has a 17 degree here. But we did not change the initial shape, but we just changed the constitutive law that defines the fiber angle. So we changed the fiber angle from 0 to 45 degree every like 4 degree. And here is the result of the change in the vertical thickness. So we calculated the vertical thickness by using the threshold value from the 0.5 millimeter. So we calculated this line with 0.5 millimeter, and we defined the vertical thickness from here to here. And the color shows the vertical thickness, and here we plot a map with horizontal axis with muscle activation, the vertical axis is the fiber angle. And as you can see that the vertical thickness was significantly increased when the fiber angle was like 17 degree to 31 degree in the male larynx. And in the female larynx, the maximum the vertical thickness appeared at the 31 degree. So we could observe that by changing the fiber angle, there's large increase in the vertical thickness also in the male larynx. So here you can clearly see how the vertical thickness was increased. So from when the fiber angle was 0, the the deformed shape was quite similar to the initial shape shown in the black line. But if the fiber angle was like 17 degree to 31 degrees, this vertical thickness, so it's the lower part of the vocal folds going towards the medial plane and going towards the center line, and you can see this vertical thickness was increased here. But if the fiber angle was reached 45 degree, the vertical thickness was slightly decreased from the angle 31. And here's a comparison between the experiment and simulation. And in the previous experiment, we observed the change in the vertical thickness at the center. And this is a simulation. As you can see, the lower part of the vocal folds going towards the center line, and the center part of the vocal folds here. You can see how the vertical thickness here was increased in the simulation. And here is the result of the female larynx, and this is quite similar between the male and female, that the angle was 0, the deformed shape was quite similar from the initial shape in the female. but fiber angle was increased to 31 degrees. The lower part of the vocal folds going towards center line, and the vertical thickness was increased as observed in the previous experiment. So by doing the mechanical experiment, we can, the good point is that we can discuss why this change in the vertical thickness occurred in different fiber angle. So here we visualize to explain why the angle 17 has a larger vertical thickness. So we plotted the displacement direction in each element with the vocal folds here. And here's the angle 0 and angle 17. And here we can clearly see the difference between 0 and 17 at the rotation the itinerary here. As you can see, this red arrow showing the rotation, the clear rotation the itinerary here, but this arrow shows more like rigid translational motion of the itinerary here. So this displacement was caused by the expansion and compression stresses. The blue and green arrows show the expansion and compression principal stresses. And here, by changing the fiber angle, the orientation of the distress was different between angle 0 and 17, and this caused the rotation of the itinerary like this. And this realized the change in the vertical thickness in each larynx. So when we consider the implication of these results, first, the observed change in the vertical thickness here, as shown here, could significantly affect the voice quality as I described in the beginning. Like when we have the thin vocal folds, the vocal folds cannot close completely and the voice becomes very breathy. And when the vertical thickness is very large, the voice becomes very pressed voice. And this kind of change in the voice quality can be realized with the difference in the fiber angles. And when we consider such difference in the fiber angles, we can maybe explain why we have different voice control ability. As observed in the difference of the male and female, they have the different fiber angle. So each person may have different fiber angles, and this can explain why each person has different voice control ability. So in the next study, we have to observe how muscle fiber orientation varies among the individuals. And also these results suggest that maybe strengthening the TA muscle, the vocal fold muscle, enables more precise control over the voice quality. So here's a summary of this study. So this study explores the physiological mechanisms contributing voice quality control and the differences in individual voices using computational muscle modeling. And the results shows that the variation in muscle fiber orientation significantly influenced the vertical thickness of vocal folds. And this change in the vertical thickness had a large impact on the voice quality control. So this is the end of the study presentation. Thank you very much for your attention.
Thank you. So we are open for the questions. If you have any, just come online and ask. If you prefer not to come online, you can type it into the chat. Anyone?
Hi, this was super interesting. Thank you, Dr. Yoshinaga, for this presentation. I'm interested in this idea of the different fiber alignments as potentially causing or allowing different voice effects. And I'm wondering if the MRI technique is able to detect differences in those fiber alignments, and maybe if there are particular exercises or vocal function techniques that people can use to preferentially strengthen in different directions.
Thank you for the question. So first, I show the MRI image, super resolution MRI image. So this is, it took so long time to get this resolution MRI, but you can slightly see the angle of the muscle fiber here. And so maybe if we can use this kind of MRI technique, maybe we can observe the difference in fiber angles in each larynx. But this is extracted larynx, so we cannot get such high resolution MRI for the living person. So this might be the future work, but yeah, at least we can observe the change in the fiber angle between these male and female larynx in this study.
Yeah, thank you.
Hi, thank you so much for the lovely talk, Dr. Yoshinaga. I'm particularly coming from this from a perspective of trans voice training, where basically a lot of the manipulations that's done for people that are trying to manipulate the gender perception of their voice tend to focus on combining oral and laryngeal vocal tract size along with this sort of TA muscle manipulation to generate different types of perceived gender of voices in addition to different types of voice qualities. So I'm particularly interested in your in the topics that you're planning on exploring about the limits of these sort of manipulations that people can do with their voice. And I'm curious if you have a hypothesis or just a general inkling for what are the exact, I mean, a vague question, but what are the limits of manipulation that someone can do with their voice? And do you think that those are highly individual, or do you think people can train to produce a wide variety of voices given enough time and pedagogy?
Thank you very much for your question. So yeah, we only did this study for the 2 male and female excised larynges. So we only know that there are differences in this male and female, and if we consider other the individual differences, it will be the very hypothesis. But there are several factors considering the change in the vocal fold shape, and the first is muscle strength. We define the maximum stress which can be changes the shape of the vocal folds. So by training the vocal fold muscles, then you can change this maximum how the fiber can produce the stress in each muscle, and this can change the limits of how we can change the vocal folds. And yeah, maybe if by training such with voice training, maybe we can change the I don't know, maybe that will be the main factor of changing the limits of each person's voice control ability. Did I answer your question?
Yeah, great, thank you.
Patrice, yes.
Yes, thank you very much for this talk. Throughout, you've referred to your 2 samples as male and female, but I noticed they also differed by 25 years in age. One of them was 82 years old. So to what extent do you think the differences could have been aging differences rather than male-female differences?
Thank you for the question. So yeah, we realized that there is quite age differences between male and female, and also the like initial shape of the female is a little bit like different between from the male, because like female has already like large particle thickness compared to the like normal human or like observation in the other ranges. So maybe this like age of 82 is a little bit special to like do the simulation, and if we can obtain the more younger female then data, then maybe we can get more similar result with the male. But this is also the hypothesis, and we only have these two data. So maybe if in the future, if we can get more data, then we can explore more about the age difference and also the male-female differences. Thank you.
I have a question. So this data is out of some patients, or were there any conditions with that already, or
I
they?
heard they are normal. They had no like speech disorder, but they are like extracted from the dead body. So
Okay.
like so they extracted this larynx from the dead body and put in the cylinder, and they put in the MRI machine to obtain this geometry.
The question is when you see many male, they have the voice of they sound like female voice, and many females, they sound like male.
Mhm.
Maybe their organs are like different. Uh,
Yeah, like if the female had like if the female is older, then like voice become like male, and like you maybe yeah, this simulation can explore such difference, but we only did the observation in the shape change the vocal folds, and yeah, if we can do like in the future like do the simulation with the vocal fold vibration, and if we can know how each larynx has a different voice type, we can explore the like change in the voice quality in male and female.
Thank you. Anyone else? If not, let's thank Dr. Yoshinaga. This is a really wonderful talk.
Thank you very much.
And thank you for joining. I hope you will join us again next month. I will be sending out the announcement for the presentation. And I hope you have the rest of the day, good rest of the day. Thank you. Thank you. Thank you, Tsukasa.
Thank you very much.